12.3 still. I hope you finished up 12.2 okay. So our homework will be 12.3 and 12.5 will be due on Tuesday. Just plan to get through today. 12.3 and 12.5. And we're talking about geometric sequences and series. So let me give you the formula. Again, it's for geometric, it's a sub n is a1 times r to the n minus 1. So remember, so last section 12.2 was arithmetic sequences and series. Now we're doing geometric sequences and series. Are you clear on the difference between them? Like if I give you, let me just make a list. If I go, let's start 2, 5, 8, 11, 14, versus if I go 2, 6, 18, 54, 100 and something big, 162, All right, so this one, this first one, what kind, is that arithmetic or geometric? Arithmetic. Why? Because every time it is adding 3. If you're adding or subtracting the same number every time, you're in arithmetic sequence, huh? That was section 12.2. And we had an a sub n and an s sub n formula in that section for arithmetic sequences. That was last night's homework, right? And now this one is geometric. Why? Because it's going times 3, times 3, times 3, etc. So when you're multiplying or dividing the same number every time, that's called geometric. And we're going to have an a sub n and an s sub n formula in this section. This is 12.3 for geometric sequences. In fact, there is the a sub n formula for geometric for this section 12.3, which is what we're dealing with. So I'll give you all 4 formulas right at the top of the exam 4, which is the week after next. Bless you. They'll all be up there. All right, so let's use it. It's saying A1 is negative 7, R is negative 8. So I'll use this formula. AN is A1, negative 7, times R, negative 8, to the n minus 1 power. We good to there so far? Now, what do they want me to find? A sub 5. So plug in the 5. Goes up minus 8 to the 4. And that's some big number. Somebody have that one? 28,000 something, I'm thinking. See if I'm in the ballpark. 28,000? Negative, I mean? No? Times the 7, though, right? In the front? 28,672. Thank you. So there it is. There's the 5th term in that geometric sequence. They get big fast in the geometric sequences. Does that make sense on that? Questions on that? We good? So again, we have geometric and arithmetic. Last section was arithmetic. This one's geometric. We have an a sub n, s sub n formula for each section. They'll all 4 be at the top of the next test. All right. Let's try this one. Well, that's the same thing now, isn't it? 5th term. Yeah, let's do something different. How about this one? This one looks good. They want the nth term formula, and then they want the 5th term. So try that one. It's geometric. Again, they're telling you geometric. So give that one a try. So a sub n is a1 times r to the n minus 1. So A1, they're calling it A in this problem, but it's the same thing as A1. You can tell, because up here it says initial term A. So I don't know why they're suddenly making it A instead of A1, but it's the same thing. So root 6 times root 6 to the n minus 1. So there's the general formula. I think they asked that in part 2. They asked for the general formula. Now they want the fifth term. So put in a 5. Good so far? Now how do you do root 6 times root 6 to the 4th? Well, it's a bunch of root 6's, huh? So it's 5 of them all together, right? 5 root 6's all together. Now, every 2 root 6's, you can underline any ones you want, but every 2, what is root 6 times root 6? Plain 6. It's root 36, right? 2 of them make root 36, or in other words, plain 6. 2 of them make root 36 or plain 6. And the other one just stays root 6. So in the end, 6 times 6, 36 root 6 is the answer. Does that make sense? With all those roots? Right, so when you got 5 roots of 6, every 2 of them, 2 root 6's make a regular 6. 2 root 6's make a regular 6, right? And then the fifth root 6, the other root 6, has to just stay root 6. So we get plain 6 times plain 6, 36, and the other root 6 is just staying root 6. No questions? All is well? All right. Let's try, find the indicated term. They want the fifth term. Okay. So they're given, this time they're giving us a sequence, geometric, 2 2/5, 2 25ths. So take it from there. ... So can you find the formula? Well, actually, you know what? We don't even need the formula. Look, they're only asking us for the fifth term. It's only 2 more jumps away. Probably be quicker just to do it by hand than finding the whole formula and then plug it in the 5. You know what I mean? I mean, you can do that if you want to. But if they're only asking me to go like 2 steps down the line, I'm just gonna do it by hand. If they wanted the 73rd term or something, then yeah, the formula would be a quicker way to go. But if they just want 2 more jumps, can we just figure it out ourselves by hand? Like what's happening? All we need is that term, huh? Right, here's the first term, second term, the third term, the fourth term, and the fifth. They want the fifth. It's only 2 more jumps. What's happening every time? What happened to make it change? The bottom's just going times 5, huh? So just do it again. Times 5 on the bottom, that'd be 125. The top just stays 2. One more time. Times 5, that's what, 625? Over 2, we're done. Quicker than doing the whole formula. So if they just ask you to go a couple places, which they often will in this section, in the geometric section, because they get so big so fast, they usually won't ask you to go very far. So you might just do it yourself, a couple jumps, save some time. That good? All right. And that's all they're asking. They're not even asking for the end formula, right? It says all parts are showing, so there's no more to this question. That's it. Okay, let's try this 7th term. You could just take a few more jumps, right? It's 2, -10, 50, that's the first, second, third. They want the 4th, 5th. Well, actually, all they want is the 7th, huh? They want this one, the 7th term. Can you find that? Can you tell what's happening? Give it a try. See if you can see the pattern. What's happening from term to term, and just use your calculator and do a few more jumps, a few more terms, rather than finding the whole formula. So what's happening from term to term here? It's times -5 times -5 times negative 5, would that be negative 250? 50 times negative 5 is some really big number, minus 1250 times negative 5. Oh, wait a minute, I'm doing the signs wrong, aren't I? This would be plus, shouldn't it? And this one is negative 6250.
Yes.
And the last one's going to be plus something too big, 31,250.
Yes.
I'm off the screen, huh? So, seventh is 31250 positive. Is that good? Just use your calculator, times negative 5, times negative 5, times negative 5, times negative 5. You go from the third term to the seventh. We good? All right, slow me down if I'm going too fast. I'm going to keep moving. All right, let's try that one. 10th term. Yeah, see if you can follow the pattern there. So it's 0. Say, let me space it out for us a little bit. So it's 0.7. It's 0.07. 0.007. You want to go all the way to the 10th term. So we have the first term, second term, third term, all the way to the 10th. I wouldn't do all the ones in between. Can you just jump to the 10th by using the pattern? Can you do that? For example, what do I mean by using the pattern? Well, you want the 10th term, right? Look for some relationship between this number and the number of zeros. This number and the number of zeros. This number and the number of zeros. You see the pattern? That number is the number of zeros if you count the 0 in the front. So if the first term has 1 0 and the second term has 2 zeros and the third term has 3 zeros, then the 10th term will have 10 zeros, right? One of them in front and then 9 behind, huh? 1, 2, 3, 4, 5, 6, 7, 8, 9, and a 7, right? 9 zeros after the decimal and 1 0 in the front of the decimal, huh? It's got to. Math is patterns. Math is totally just patterns. Everybody good with that? No formula, no steps, just a pattern. That is math. The better you get with patterns, the better you will be at math. That is math. That is totally math. Math is just simply patterns. Getting better and better at seeing them, predicting them, describing them, following them. That is math in a nutshell. Patterns. All right. We good with that? That all making sense? Let's try... all right, yeah, formula for the nth term. Yeah, see if you can come up with a formula there. It's another geometric. 5, 20, 80, 320, dot, dot, dot. So this time we're going to have to do the formula. No more shortcuts. We need a formula. So it's a sub n is a1 times r to the n minus 1. That's the a sub n formula for geometric. Right? What's a sub 1? That's the first term, always in all these formulas, huh? 5. Is that good? What is r? Yeah, remember what r is? R, how do we find r? R is always what's causing the jump, huh? What's happening from term to term? What is happening from term to term? It's going times 4. So that's your r. If you're ever unsure of r, remember how you can find r? If you're ever unsure? What does r stand for? Ratio. And it means you can just take the second term over the first term, or any term, divided by the previous term. It's a common, consistent ratio. So if you're ever unsure, this one's pretty easy to see, but if on a harder one, they're common, harder ones, you can just grab the second one over the first one, 20 over 5, and go, oh, look, it's just 4. Which, that's r, we already knew. So it's 4. Okay, now, n minus 1. Excuse me. So 5 goes there, 4 goes there. And we're good. We got the formula. Questions on that? All's well? All right. All right, try that one. Another formula. They want another formula from you. So a sub n is a1, r to the n minus 1. What's a1? First term, -1. Okay, now r, if you're not sure, remember how you can find r. R is always second term divided by first term. So second term, 1/4 divided by first term. So it's -1/4, isn't it? That's what's being multiplied every time. It's times -1/4. That's why it became back to positive, and then it goes back to negative, and then back to positive, right? Because it's multiplying by -1/4. So the r is -1/4. So put in a -1 and a -1/4. Good? We're whipping these out. All right. So now they're giving me, find the nth term. A sub n, the geometric, where r is the common. So they're giving me the a7. That's weird. They're giving me the r. So this is a little different now. So and what they want is they want the a sub n formula. So let's write that. A sub n is a1 times r to the n minus 1. So they want that general formula. That's what they want from me. They're handing me the r, silver platter, no mystery with the r. They're handing me the r. That is the -4. Good to there so far? So the trouble then is, what's a1? You with me? I need to find a1, and then I'll have the whole formula that they want. This is what they want from me. I basically got it, except I don't have a1. I need to find the a1. And then I'll have their formula. So what do you do? Yeah. Good. Everybody seeing what you do there? Take the 7. Say, oh, a sub 7 is a sub 1 minus 4 to the 7 minus 1, and that equals 4096. Does that make sense? That's what this says right here, right? When you plug n equals 7 in, a sub 7, it'll equal 4096. So now solve that little equation for a1. Can you do that? So this is what? Some big number, huh? Minus 4 to the 6. So it is 4096. Oh, that's convenient. So a1's just 1, huh? So a1's just 1. So in the end then, a1's not our answer, it's part of our answer. What's the final formula then? Well, here's the formula. It's a1, which is 1, times minus 4 to the n minus 1. There's the formula. So I guess we don't even need that 1 in the front. Is that good? Put that in right there. Because the formula is right here, which is now here. Questions? Is that okay? You guys are so quiet. I never know if I'm racing ahead too fast. If I need to slow down, let me know. Feel free to slow me down if you got comments or questions, or I'm just racing too fast. All right. So number 16, they're giving me a2 and a4, And again, they want the formula, the a sub n. So they want the a sub n, which is a1 r to the n minus 1. So they want the a sub n formula. They're giving me a2 and a4. That's kind of weird. A2 and a4. I don't know. What do you guys want to do? There's a couple of ways. How about I show you two different ways to solve it? I really don't know which one you're going to like better. We can just do the plug-in thing. They're pretty even in how good the methods are. So first off, I can just plug in the 2, kind of like we did last time, right? And that's equal to 5. Good so far? I just plugged in the 2, right? Because a sub 2 is 5. Plugged in the 2, said it's equal to 5. Then I could plug in the, what's that, 4? Plug in the 4, and that's equal to 1280. Like that. Let me clean that up a little bit. So that's A1R is 5. And this is A1R to the third is 1280. Huh. Good there? This making sense so far? So what am I going to do now? You tracking with me so far? Is it making sense what I've done? Just plugged in 2 and plugged in 4. And so now I've got this and I've got this, which is 2 equations with 2 letters. But I can't really do the addition method because they're not like terms. They're not going to combine. You see what I mean? Even though it is 2 equations with 2 letters for which we normally do the addition method, we can't do the addition method here. These are not like terms. There's no way they're going to like subtract each other and cancel or anything like that. You could do substitution. Yeah. Yeah. You could. Like plug in for R or A1, huh? Yeah, that's a good idea. Let's do that. Good idea. I was just going to divide them, which would work too. But anyway, I like your idea. So let's do that. Let's divide. So A1 is 5 over R. Just take that first one and solve for A1, right? And then plug into the other. Good idea. We're doing the substitution method, right? So A1 R to the third is 1280. Plug that in for A1. So 5 over R to the third is 1280. Everybody tracking with me? It's a good idea. Do substitution, right? Just solve for R. Or you could just, no, I solved for A1. You could have done either one. Solve for A1, solve for R, whatever. In one of them, plug into the other. And then, now, what does this lead to? What do you do with 5 over R times R to the third? This cancels BR squared, so it's 5R squared is 1280. That good? Divide by 5. Go with it, 256. And then root it, 16. R is 16. And now that we have R, we can get, because we need A1 also. So we've got R. So bring it up here and plug it in. So we've got A1 times 16 is 5. Divide by 16. A1 is 5/16. So then our formula is A1 5/16 times R 16 to the n minus 1. There it is. Not okay, I kind of traveled all over the place on that one, up and down and right and left. Does that make sense? Did you follow me? Questions I can answer? So I basically plugged in 2 and 4, and they were equal to 5 and 1280. Got these two equations with 2 letters, did substitution. Solve for A1 in the first, plug it into the second, cancel, R squared, root it, R is 16, plug in the 16 back into the first equation, A1 times R is 5. Solve for A1. A1 is 5/16. There I have it. There's my answer right up here. Because it's A1 times R to the n minus 1. A1 is 5/16. R is 16. Okay, so that's kind of tricky. A little more tricky there. All right, now we're getting to a sum. Yeah, notice we shifted gears right there. Did you feel the shift? The car just shifted gears. We're talking about sums now. Now we're adding them up. We're not just listing them, right? We're interested in what do they all add up to be, so we're going to use the S sub n formula. Just like in the last section, we had A sub n and S sub n for arithmetic in 12.2. Now in 12.3, geometric, we have A sub n, which we've just been working with, now S sub n. So we need a new S sub n formula, and I'm trying to delay and hoping it'll come to my mind. It's, oh, here it is, A1, 1 minus R to the n over 1 minus R. Is that right? Oh, I'm going to look up my notes. I'm pretty sure that's right. I don't want to give you the wrong formula. Let me see. Yeah, 1 minus R to the n over 1 minus R. Yeah, that's it. Okay, good. So there it is. There's the S sub n formula for geometric in 12.3. Again, I'll give you all four of these on the top of the next exam. A sub n, S sub n for the last section, 12.2, and A sub n and S sub n for this section, 12.3. So there it is. Let's use it. Here we go. That's the sum of n terms. That's the adding up, the totaling up of n terms. A1, what's that? First term, like always, 1/5. R. Now, R is a little more tricky to spot in this one. Can you tell? What is R? Just by looking. Can you tell? What's making the jump from term to term? Is the 5 changing, or is it just always there? Yeah, the 5's just always there. He's not making a change. He's a permanent fixture. What's changing from term to term? They're multiplied by an extra 2 on the top. The R is just 2. You might have trouble recognizing that, though, so that's why I want to give you the other option. What can you always do in case you're not 100% sure? R is always second term over first. Remember, it's a common ratio, a dividing. So second term, it's 2/5 over first term, 1/5. Remember how you do fractions over fractions? One on the bottom flips up, huh? Like a high diver going upside down. Like that. And so we get 2/5 times 5 over 1, cross cancel. So like I was saying, R is just 2. So if you can just see it, great. You can say it's just 2. If you're not sure, do the second term over first term and you'll get it. So R is 2. Coming back over here, R is 2. So I filled in R is 2 and 2. So there's my formula, except, no, that is my formula. That is my formula. Yep, that's my formula. Well, no, back to my except. Except, this is fine with me on a test. Give me that answer, you got it. But they want a certain look. So to make Math Excel happy, we have to kind of move things around a little bit. But in a test, I don't care. In fact, there is something they're going to almost always want you to do. So let's just get in the habit right now and make things a little easier. They're almost always going to want you to subtract these guys and multiply the total over there. So 1 minus 2 is -1. Times the 5 over there will be like that. See what I just did? That's pretty standard procedure. What they almost always want you to do is just subtract down there in that denominator and then just multiply those two denominators together. Right? That's just multiplying fractions, top times top, bottom times bottom, right? I just did, 1 times the top and 5 times the bottom. 5 times -1 is -5 down there. Good to hear so far? Now, again, that would be fine answer by me on the test, full credit. But they're being a little more picky. See what they've done? They're saying, give me something in the front, and then give me something with the n coming first. They're just being picky. They want me to take this and switch the order and put the n in the front. Now, can I just switch the order without changing anything else? No. that changes the sign. Are you aware of that? When you switch the order of subtraction, you ever thought about that? If you have two numbers and you're subtracting them and you switch the order, it doesn't make like a totally different number, right? It's not like 4 and then like 11 or something. It's -4, huh? It just changes the sign of the answer, doesn't it? So if you switch the order in which these are subtracted, you have to switch the sign in the front. What sign was in the front? Negative. Now it's positive, or regular. There's the answer. In the form they want. Does that make sense? Turn around on the inside just because they asked you to put the in the front. So then the final answer here would be 1/5 here and 2 to the n minus 1 there. Good? On the S sub n formula? Was that fun? All right, let's try another one. Oh yeah, what do you do with that? We had that in the last section. The big Greek S, the sigma, capital sigma, the big Greek S, right? What does that thing mean? When we see the big Greek S, we realize we're going to need the English S, the S sub n, right? It means sum, doesn't it? So we're going to use the sum formula. Again, A1, 1 minus r to the n over 1 minus r. But it'll be helpful to first crank out a couple terms, won't it? Remember what we always do? We take the formula 8/9 to the k, and we let k be 1, k be 2. Probably that's enough. Just get a couple terms so you know what that thing's doing, right? You know what you're looking at. So if you plug in 1, you're going to get 8/9 to the 1, just 8/9. If you plug in 2, you're going to get 8/9 squared, which is some big number. So 64/81s, I can do that. 64/81sts. Anyway, and on you go. And we're adding these, aren't we? Am I going too quick? You okay with Greek sigma notation, the big capital S? Big Greek S, right? It means take that formula, take whatever formula is next to the big Greek S, this, 8/9 to the k, and plug in k is 1, k is 2, and on you go. See what you get, 8/9, 64/81st, and put plus signs. Why plus? Because that's a Greek S, means sum. Add them up. Put plus signs between them, right? That's what that symbolism means. Okay, so we've done all that now. Now, can we get a formula for the sum, for the S sub n? Well, yeah, it's A1. What's A1? Yeah, 8/9, right? First term. What's R? Can you tell what R is? What is it? It's 8/9 also, yeah. If you're not sure, just go, remember it's second term over first. So second term, 64/81s over first term, right? Flip this guy up, becomes 9/8 times. Remember high diver upside down? Like that. So R is 64/81s times 9/8. 9 goes in 81. 9 times 8 goes into 64. 8 times, it's 8/9. So the R is also 8/9. The R and the A1 are both 8/9. We good to there so far? It's a little mess. We're going to have to clean it up. Okay, so what are we going to get this out of the way here? What are we going to do with that? So right now we're here. So what we usually do first is we subtract this and bring it over this way next to that guy. So what is 1 whole pi? 1 whole pi take away 8/9 of a pi. I ate 8/9 of the pi. How much is left? 1/9 of the pi. So this is 1/9 down here, isn't it? Right? 1 whole take away 8/9. Leaves you 1/9. And then what do you do with fractions in the bottom of a fraction? High diver flips upside down. We can put it in the front instead of in the back. It doesn't matter, right? So I'm going to put it in the front. So it'll be 8/9 times 9 over 1 times 1 minus 8/9 to the n. Are we good? Are we happy? So far so good. See where I took this 1/9 and brought it up here. To be 9 over 1, cancels. 8 times 1 minus 8/9 to the n. And that's all they want. This time they're letting me have the n in the back. So this is 8. This is 8/9. Done. Yeah.
When you did that, why were you able to do that if that was the exponents on the parentheses?
So the exponent is on this 8/9.
Right.
It's not in anything else.
Right, so how do you subtract it first?
What do you mean? Alberto, where am I subtracting first?
You subtracted 1 minus 8/9.
Oh, down at the bottom. And you're saying, hey, that's the power. Yeah, but the power's not on these guys, right? Alberto, are you thinking order of operations?
Oh.
Is that what you mean? Or?
I listened.
Yeah, it's okay. Yeah, I can subtract this at the bottom because it's totally separate from that other power stuff. Yeah. So I just subtract these on the bottom, 1/9, and I flip that up. Is that good with everybody? Does that make sense? Any other questions on that one? That okay? Right, it's kind of a mess. Can you tell what happened down there, right? Here I subtracted, got 1/9, brought it up here, came 9 over 1, canceled, 8 in the front. So that's what we always do on this S sub n form is subtract the bottom, get the answer, flip it up next to this guy, and cancel. All right, let's try another one. They're a little messy. Let's try this one. So we're going to use the S sub n formula, which is A1 times 1 minus r to the n over 1 minus r, right? All right, what's A1? First term, -1. And what's R? +7, huh? Everybody seeing that? If you're not sure, go over on the side. R is second term over first term. Second term is -7. First term is -1. It's +7. So +7 to the n power. Good like that. And so what can we do with that? This is -6, right? Subtract those. And then, well, I don't want to go too fast. Everybody good to there? Everybody okay with this? Now, we got to bring this guy over. Where this guy's going to come over where? Well, this is over 1. And so we just multiply. This times this, this times this. So it'll basically become -1 over -6, 1 minus 7 to the n. Well, I guess, yeah, that's right. And the two negatives become positive. That okay? See what I did there? Right, so again, these denominators, we always subtract them and bring them over, don't we? 1 times -6 on the bottom made -6. I just left that -1 on the top. And then 2 minuses cancel. Is that okay? No questions? Yeah.
If you're multiplying the -1 in the numerator by the numerator on the other side, would that change the positive side?
Yeah, so that's another way you could do it. Instead of leaving the -1 sitting here, I could have multiplied it in and that would have turned it around. And then you could have done that. Here, let me just go back. You could have done that. And so that would have turned it around and then just left a 1 on the top and a -6. So these are two versions of the same thing. Does everybody see that? See how this is +1/6, that's negative. The reason this is the same is because that negative went in there and turned that around. Or vice versa, these negatives went in, whatever. Yeah. One, other questions? We good? All right, let's try here number 20. So again, the S sub n formula, which is A1, 1 minus r to the n over 1 minus r. A1 is 1/9 times. Can you tell what r is? It's 8, huh? If you're not sure, again, just go second term over first. It's 8/9 over 1/9. Flip up that 1/9 to be 9 over 1. And it's 8. So, everybody okay with that? It's just multiplying by another 8 every time, isn't it? The 9 is a fixture. It's just there. But what's changing, jumping from term to term, is an extra 8 on the top. Good? And then just multiply, well, this could be -7, so it'd be 1 over -63. 1 minus 8 to the n. We good to there so far? Same kind of thing as usual. Just multiply those two denominators, huh? Now, what's all this? What are they wanting me to do here? They want me to actually plug in an n now. Now, what is n? I'm going to plug in the n here and then use my calculator to find out which of those answers is right. See how this formula didn't just end with an n. Look back. Let me look back with you. See how this last one? Well, we can't see anything yet. This last one ended at n minus 1, right? And the one before that ended at, well, it just had a bunch of n up here. Was that kind of notation? This one, n minus 1. See how they've been ending arbitrarily at some n or n minus 1 value, not at a definite number, right? Whereas this one, he's like, I'm stopping at 13. So we have a definite stop to him. We can add him up. So now, what do I plug in for n? Careful now. Be a little careful. Before you say 13 too quickly, think again and think carefully. What is n in all these formulas we've done these last two sections? What does n represent? N is the number of terms, right? Hasn't n always been the number of terms? That's what it is and always will be. So as you look at this, let me ask you, are there 13 terms here? There's 14 terms, right? Because this is first power right here. Right? So right here is 13, and this is one more, 14 terms. Right? So be careful. N is 14. N is the number of terms. It's not just that last power. It's the total number of terms. Always, in all these formulas, N is the total number of terms, which is actually 14 terms up there, isn't it? So 14 terms. So plug in 14 there and hit the buttons on your calculator. So you get, thank you, 6.98 blah 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 blah. Well, I'll do the blah 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 blah. 102.6208 with a little 10 in the upper corner. Thank you, Terrence. Right, which means that little 10 means times 10 to the 10th. It's scientific notation. So it is this answer, right?
It shows times 10 to the 10th.
Yeah, on yours it does, yeah. Is that good? Times 10 to the 10th, scientific notation. What does that times 10 to the 10th mean? It means the number's not really 6.98. It means take that decimal and go 10 places to the right. It's a really, really big number. Bigger than the trillions. Bigger than the national debt. Right? It's really, really big. Right? We good with that? That makes sense on that? Question? If you have trouble getting that on your calculator, grab me after. Be glad to help. Let's try this one. All right. So now we're talking about, notice the dot, dot, dot. That means it goes and goes and goes and goes. All right. So we have a special formula for that. It's called S sub infinity. So this one doesn't stop after 5 terms or 10 terms or even 1,000,000 terms. It goes forever. It's an easier formula, A1 over 1 minus R. I'll give you that one also. All 5 of these will be at the top of exam 4 week after next. So you don't even have to put them on your 3x5 card. You have an A sub in and an S sub in for last section, an A sub in and S sub in for this section, and an S sub infinity. And it's only true for R between -1 and +1. When R is not between -1 and +1, then it diverges. That's when you would choose this series diverges option. So the series diverges if the R is not in there. I'm not sure you know all what that means, but I'll explain. But for now, there's the formula. As long as the R is between -1 and +1, then that will be the formula. Otherwise, you just say it diverges. Okay, so let's give it a try. So, looking at this series here, what's A1? So S sub infinity. Oh, and how would I know on a test, week after next, that I'm supposed to use the S sub infinity formula and not one of the other formulas? What's going to tell you that? The dot, 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 right? That means it goes forever, right? Okay. So, S sub infinity. A1, what's A1? 1, first term, always means first term. 1 minus, over 1 minus R. Got to get R. You know how to find R. What's R? Always? Second term over first. What's the second term? A half. Over first term 1. It's just a half. R is a half. Is R in the zone? This zone. Is a half between -1 and +1? Yeah, absolutely. Right? Put them on a number line. Got -1 here. Got -1 there and +1 there. A half's, here's 0. A half's about right there. It's in the zone between -1 and +1, isn't it? So it's good to go. So it's okay. We'll say the R is okay. R is okay. So that means I can use the formula. Otherwise, you can't even use the formula. I mean, you should not use the formula. You can. You could plug in and get a number, but it's a lie. It's not the truth. The formula is just lying to you. So if you get an R that's outside of the -1 to +1 zone, don't plug into the formula. Just say the series diverges. Okay, so what do we get here? This is 1 over a half. 1 over a half. And then what does that do? What does the fraction on the bottom do? Flips up. This becomes 1 times 2 over 1, which is 2. What do you think of that?
Do we need to go that far for this?
Go that far?
Because it says all parts showing, so.
Yeah, that's what they want. They want the series converges to 2.
Oh, I see. I didn't see that.
Yeah, that's what they want. So what do you think of that answer we just got? Do you believe that? I think so many times we could just do these math problems, next problem, next problem, next problem, next problem. Get that homework done, all right. But hold on. What did we just say there? 1 plus a half plus a fourth. What would be the next term? An 8th, 16th. For how long? Forever. Really? Okay, here we go. We got to spend 5 minutes being real. We can't just fly over this and say, oh yeah, that's true. I always knew that was true. Really? What if I say, okay, I'm going to throw trash in the trash can over here. And I'm going to, maybe I'll set up a robot, to program a robot to throw trash in this trash can over here. Every 10 seconds, the robot will throw a piece of trash in the trash can. Okay? And could it do it like every 10 seconds, like all day long, and not overflow the trash? Is that possible? Yeah, it's real small, right? Sure, a little teeny tiny sliver. You know, or a robot, every 10 seconds, throw a little sliver, 10 seconds later, little sliver, 10 seconds later, got a little bigger that time. Little sliver. All right, just every 10 seconds, a little sliver. So, every 10 seconds, all day long, night and day, one whole day, you know. Yeah, it wouldn't be full of trash, you know. And how about if I let the robot go all week? Can you have a small enough sliver? Yeah, sure, probably. How about all month? Every 10 seconds, all month long. Yeah, it's really, really. How about all year? Every 10 seconds. Well, yeah, if it's just really tiny, all year, won't overflow the trash. How about for a decade, 10 years? Every 10 seconds. Well, it's got to be a pretty small sliver at this point, but I guess technically, 100 years, a century, a millennium, 1,000 years, 10,000 years. Is it possible? Well, yeah, it'd have to be like really tiny. Every 10 seconds, 10,000 years, not overflow the trash can. Now the question that's asking. Forever. Not just 10,000 years. That's just a sliver of forever. Forever. It throws trash in the trash can forever and doesn't overflow the trash can? Is that possible? That just said yes. Do you realize that just said yes? But you don't think yes, do you? Do you realize that wasn't hitting you real, was it? Until I just did the trash thing, right? That just said you can add up positive numbers forever and get a finite sum too. That's what that just said. I want to make sure math's hitting you real when you're doing math. That is the number one. If somebody was to ask me, what is that drama? Is it dramatic for my presentation? I asked if I played a drama, just to, heighten the drama. If somebody was to ask me, after 20 years of teaching math, what separates math people from non-math people? Or what can I do if I want to be more of a math person? Those people that just seem to know quicker than other people, And I'm not sure it's easy to change it. I'm sure it's not easy. I'm not sure it's even possible. But I know what it is. I'm pretty sure what it is over the years of watching people and working with even my own kids, homeschooling them, and see if different ones are quicker at math than others. Math is more real. It's more real to the people that are the math people, so to speak. They don't just read a question like that and it's just numbers on a page, move the numbers around, boom, there's a number. They're looking and they're thinking, that's like a 1 whole pie, and then a half a pie, and a fourth a pie. And that's 2 pies? Really? That's the kind of way they're thinking. It's always real things to them. Try that more and more. More and more, try to make math real for yourself. As you don't just see numbers on a page, think a whole pie or a whole paper. How about I do that? 1 whole paper. Okay, robot, throw 1 whole paper in the trash the first 10 seconds. Okay? And then 10 seconds later, throw what? A half a paper. A half a paper in the trash. Right now we got a paper and a half in the trash. 10 seconds later, throw half of the half, a fourth of the paper in the trash. 10 seconds later, what's going to come next? 1/8, right? Half of the fourth, right? So notice it's cut in half every time, huh? Right? The R is a half, isn't it? It's just halving the paper every time. 8, there's an 8, and there's now 10 seconds later, roll on to 16. See, it's just going to keep going like this, huh? Half of the paper, half of the paper, half of the paper, half of the paper, half of the paper. I can't do it anymore. Half of the paper, half of the paper. Every 10 seconds, am I ever going to throw away the rest of this paper? Even after forever, whatever that means, after forever. No. If I'm not going to, right? I'm only supposed to throw away half of what's in my hand. That's just doing half of the last term. Half of what's left in your hand. That's what that sequence is saying. So I'll just keep throwing away half, and half, and half, and half. I'll never throw away the whole paper, or I didn't obey the rule. Only throw away half of what's in your hand, right? So if I do this after 10,000 years of throwing away the robot, throwing away half of the 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 half. And it's all piling up in here. Not much though, but it is in there. Half of the half of the half of the. What, after 10,000 years, how much will be left in the robot's hand? Or how about this, how much will be in the trash? The first whole paper, and then all of the second paper except for this tiny little sliver, right? One whole paper, and basically the other paper. Two papers. It's true. It's real. Let it be real for you. The more it's real, you will have a sense of what's happening in math. When you write numbers and they're real pies and papers and things to you, you will do much better at math. When it's just like, you know, I've seen my different kids. It's kind of funny. You know, one of my children was instant, quick with math, and he was always, it was real. Whenever I would do stuff with him, he'd say, well, how can I remember him asking me when he was young, Dad, I thought when you multiply numbers, they get bigger. So why is a fourth times 3 smaller? I was like, yeah, you're right. But it's a fraction, so it's a portion of it. I remember dialing at that time going, yeah, he's thinking real. He's real with it. And then one of my other kiddos, my next one down, my girl, my oldest girl, nothing real for her was ever happening. It was all just moving numbers around. And what does this mean about real? Nothing, Dad, nothing. Just tell me where to move the numbers. Tell me where to move the numbers. Anyway, and then my next daughter down, more real for her. Anyway, so the more you can make it real, I'm not sure how much that can change, but the more you can make it real for yourself, the better you'll naturally do it now. If this is real for you. So, anyway, 2 whole papers. Is that true? 2 whole papers? Now, wait a minute. It wasn't quite 2, was it? I mean, I never threw away that. I always had that last sliver. I threw away 1 whole paper, and then a half, and then half of the half of that, you know, all the way down. But I always had a sliver left. I never threw away really 2 whole papers. It was 1 whole paper, and then almost all of the other paper. But I had a sliver left, right? I never threw away 2 completely. Shouldn't the answer be like 1.99999? Why is it 2? Is that right? Is math right here?
Infinitely close to 2, right?
Yeah, shouldn't it be infinitely close to 2? I had a sliver left still. I never threw away the whole entire second paper, right? I had a sliver left. But after forever, which you can say but not really do, after forever, which you can think about and give answers for, although we can't experience, after forever, you would throw away exactly 2 whole papers. After forever. Do you get the idea? We're dealing with the infinite here. Tricky things happen. Things that don't always seem like they're going to happen. Let me do one more. I'm probably using up. I always enjoy. This is what calculus is a lot about, is thinking about these kind of concepts. Let me do one more thing, then we'll do the rest of the questions. Let me ask you this. 0.9, well, let me do it this way. 0.9 bar. What does that mean? 9's forever, right? 9's and on and on and on and on. Is that close to 1? 1.0? 1? It's real close. How close? Infinitely close. Would you believe me if I said 0.9 bar is equal to 1? Exactly equal to 1. Not different at all. Probably you might not, but hopefully now you're starting to see that the infinite is a little more tricky than you might think. I mean, who would have thought you can add up positive amounts of things forever and get a finite sum? We just proved it's true. Well, can 0.9 forever be the same as 1? It is the same as 1. It is exactly the same as 1. It is not different in the slightest. Now, how can that be? Is that true? Let me prove it to you. If they were different, if 2 things are different, if I take a 5 and a 7, they're different. How can I prove they're different? Well, if you subtract them, there's a lot of ways to prove they're different. One way is if you subtract them, you get something that's not 0, right? If I subtract 2 numbers and the answer comes out 0, what does that mean about those numbers? They're the same number, right? If you subtract 2 numbers, if their difference is 0, they're not different. They're exactly the same. So what would happen if I took 1.0, and subtracted 0.9 bar? What's the difference? Well, we can't do 0.9 bar, right? Because the 9's like go forever. I mean, where are you going to start? You're supposed to start on the right edge. I mean, what is the right edge? How do you do the right edge? Well, right, okay, I realize that's a problem. So let me do one of the 9s and kind of see if we can follow the pattern. What if there was just one 9? I know there's not one 9. But what if there was just one 9? What would 1.0 take away 0.9 be? It'd be 0.1. There would be a difference, and it would be 0.1, right? But there's not just one 9. There's infinite 9s. Okay. But what if there were two 9s, let's say? If there were two 9s, and I subtracted, there would be a difference, and it would be 0.01. Right? Those two numbers are not the same. 1.00 and 0.99 are not the same because if you subtract them, you get a definite difference, 0.01. But there's not two 9s. There's infinite 9s. Okay. Yeah. So what if there were three 9s? Well, you get the pattern. It would be 001, right? But of course, there's not three 9s. There's infinite 9s. Okay. What if there were four 9s? Well, then we would get 0001, but there's not four 9s. There's infinite 9s. Okay, you get the pattern. So the 9s go forever. So in other words, the difference is going to be zeros, zeros, zeros. How many zeros? Forever. And then, after forever zeros, comes the 1. After forever zeros comes the 1, right? So what if I said, I'm going to give you you guys are such good students. I'm going to give you $1,000, and I'll give it to you after forever. When are you getting $1,000? After forever. Never. That's another way of saying never. After forever. So when does that 1 come? After forever zeros, right? So when does that 1 come? Never. So what's the difference? 0. So what are those? The same number. Now, do you feel like I'm just tricking you here? I'm not. They really are the same. I can prove it. I'm probably using up way too much here. Let me go quick. I can prove it one other way. They are the same. They really are. 0.9 bar is 1. There is no difference. Let me prove it one other way. You might have seen this proof before. You can just call 0.9 bar, 0.9's forever. Just call it by the name X, like naming your pet, your rover. Right? So I'm just giving it a name, X, nothing magical there. And then what happens if you multiply a decimal? What if you multiply both sides of this equation by 10? This will be 10x. And what's 10 times the right side? What's 10 times a decimal number? What happens? It moves one place, right? So won't it become 9.9s forever? Right? Just moves the decimal one spot. Right? Now what if I subtract those? What's the left side? What's 10x? This is another way to prove to you that it's really 1. What's 10x minus x? 9x, right? Now, what's the subtraction on the other side? 9.9's forever minus 0.9's forever. The 0.9's forever just drop out. It's just 9, right? We good? Divide by 9. What is x? And what is x here? 1 is x, is 0.9's forever. 0.9's forever is 1. It is true. 0.9 bar is 1. It is not different than 1. Infinite does some tricky things. All right, enough. I'll enough playing around. I hope you enjoy. Do a couple of these. So do a couple more of these infinite ones. All right, so try that one. How would you recognize on the exam we take in 2 weeks that's the S sub infinity formula? What's going to key in? The dot, dot, dot. So it's A1 over 1 minus r. So find the r first off, and make sure the r is in the zone between -1 and +1. So what is r? Second term over first. Second term minus 1/10 over first is 10. Like that. So second term over first. And so what that bottom number is a 10 over 1. When you do that thing, you flip it up, right? Flip it up. So flip it up, it'd be 1/10. So then that's, what's that, minus 100th? So r is minus 100th. You can just make that minus 0.01. Might be easier to deal with a decimal, 0.01, so that's our R. A1 is 10. So what do we get? S sub infinity is 10 over 1 minus 0.01, which is 10 over 0.99. Oh, is that come out ugly? Oh yeah, I probably shouldn't have changed the decimal. They're going to make us do a fraction, huh? All right. Yeah, we better go back. All right. So I'll leave it as negative 100. So A1 is 10 over 1 minus, watch the signs there carefully. Oh yeah, I was messing up on the sign, wasn't I? Anyway, now it's correct. Right, because there's a subtraction right in the formula, and then the R is also negative. So you get the double negative, going to add thing. Just be careful, it's easy to miss that extra minus. So it's 1 plus 100. And what is 1 plus 1 over 100? Isn't 1 100 hundredths? So isn't that 101 over 100? Does that make sense? And grab that from the bottom, flip it up, right? Flip it up. And so we get 10 times 100 over 101. It flips upside down, huh? And so what is that? 1,000 over 101? That was kind of a lot of work. 1,000 over 101. There it is. There's what they all add up to be. Is that good on that? Questions on that one? I whipped that out too quick. Are we good with that? Is this off the screen a little bit? Can you read this okay? There we go. No questions? Good? All right, so try that one. How would you know you're supposed to use the S sub infinity formula on this one? Yeah, infinity at the top, huh? It's the same thing as dot, 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 huh? So you know the deal. A1, 1 minus R. So you got to find the R. So you probably need to list a couple terms. You know, let K be 1, K be 2. All right, so A1, well, I don't have any terms here. Plug in K equals 1, so 4 times 1/3 to the 1 minus 1. That's 0, so it's just 4, 1/3 to the 0. And this one's 4 times 1/3 to the 2 minus 1. So it's 4 times the third. It's 4/3. So the first term is 4. The second term is 4/3. We good with that? Because the first one had a power of 0, 1 minus 1, 0 power. So we good? 4 and 4/3. Now we got to get the R. What is the R? It's always second term over first. So R is 4/3 over 4. So that's over 1. Flip it up. So that's 4/3 times 1/4 cancels. 1/3. So the R is 1/3. So is the R in the zone? Yes, the R is in the zone. You'll say it's okay. I can use the formula. So it's A1, 4 over 1 minus R. R is 1/3. We good to there? Am I racing ahead of you? See how I did that? So K is 1. The first term is 4. K is 2, second term is 4/3. The R is 1/3. So what do we get then? So the S sub infinity is 4 over 1 whole pi. Take away 1/3 of a pi. 2/3 of a pi. Flip that thing up. 4 times 3/2. And that's over 1, right? So it's 12 over 2, 6. There it is. Infinite number of positive numbers add up to be 6. Finite sum. Surprising. Good there. Is that good? Questions? All right. Thing in this section. All right. So, yeah, basically when they give you a formula like this, if it's a linear formula, linear means if it's like m times n plus b. You know, like mx plus b, but we're using n as our x. Then that's going to be an arithmetic. I'll just give you the facts here. If it's exponential formula, like you know, the n is in the power zone, like a to the n power. N is in power. That's geometric. And if it's n squared or other things, not linear, not exponential, that's going to be neither. So there we have the 3 rules. So if it's a linear formula, it's arithmetic. If it's an exponential formula, meaning n in power, then it's geometric. And if it's n squared or other things, then it's not linear, and not linear, not exponential, then it's neither. Okay, so how about this one? N plus 7. Yeah, it's linear, right? That's linear, so it's going to be arithmetic, because it's linear. And what they want me to do is find the sum of the first 50 terms. So which formula am I going to use? S sub n, not S sub infinity, huh? Because we're not doing infinite terms, just 50 terms. Which is, that's the old one, which I can't remember now. Oh, n over 2. That's what it is. It's n over 2 times a1 plus a1. It's the S sub n from the previous section, 12.2. The arithmetic one. Is that good? So use that one. So how am I going to use that one? Exactly. What is n in all these formulas? Number of terms. A1 is the first term, AN is the last term. So what's the number of terms? Yeah, they say 50 terms. Find the first 50. So 50 over 2. Good. What's the first term? And what's the last? Well, I'll have to figure that out using the formula, huh? You know what I mean? The formula is n plus 7. So using the formula, is it okay if I come down here and erase some of this? So using the formula, exactly. Plug in 1 for the first term, plug in 50 for the last term. Exactly. So use the n plus 7 formula, plug in n equals 1 for the first term, get 1 plus 7 or 8, plug in n equals 50 for the last one, get 57. So 8 is the first term, 57 is the last term. Is that making sense? So that was the formula, n plus 7. The first term plugged in 1, last term plugged in 50, got 8 and 57. What's that? 25 times 65. Somebody got a number there? 1625. There's the sum of the first 50 terms of that formula. Is that good? Is that making sense on that? Any questions on that one? All right, let's try. Okay, so 3n squared. Is that arithmetic, geometric, or neither? Yeah, it's neither because it's not linear. It's not first power. And it's also not exponential. Now, I want to make sure you're clear on that because you might go, what do you mean it's got powers? Meaning n is not in power. Exponential is not just powers, but it's the letter in power. Like if it was n to the third, or no, that wouldn't work either. If it was, what was it? Oh, if it was 3 times 2 to the n, that would be exponential. If the n itself got into the power zone, that's what exponential. Really important as you go into Math 5A this summer or next fall or whatever. Exponential functions, their derivative is totally different formula than power functions. So you really want to have that clear in your mind. When the letter is in power, that's what we mean by an exponential function. When the letter itself, not just that there's numbers in power, but the letter itself is in power. That's a whole class of functions separate. Those are the ones that are inverses from logs, right? They're a special thing. They make the rocketing up, and they have, anyway, we can review that before the final. But anyway, yes, so this is not exponential, is it? It's just got a number in the power zone. It's not exponential. This is neither. This is neither. Now, you don't have to memorize and write in a 3x5 card my little rule. You could just figure it out yourself. You could just say, look, I'm just going to plug in n equals 1, n equals 2, and n equals 3, and I'll see. And you can just see if it's adding the same number every time, or multiplying the same number every time, which would be geometric, or neither. Right? Plug in 1, what do you get? 3 times 1 squared, that's 3. Plug in 2, what do you get? 3 times 2, 3 times 4, 12. Plug in 3. Oh, that's supposed to be squared, huh? Plug in 3. 3 times 9, 27. Now, is it timesing by 4 every time? No, that doesn't work for the second part. So it's not geometric. It's not multiplying the same number every time. Is it adding what, 9? Is it adding 9 every time? No, that wouldn't work there either. See how it's neither? So you could figure that out for yourself. You don't need my little rule. All right, that's neither. So what's that one? Arithmetic, geometric, or neither? Arithmetic. It's linear. It's like y equals mx plus b, except we're using n. It's y equals mn plus b. Right? It's n to the first power. So it's later. And then you got to find the 50 terms. I don't got time for that. Okay, so now they're going 7, 9, 12. So it's like they're putting the two sections together here at the end. The 12.2 arithmetic and the 12.3 geometric. Make sure you have the whole picture. So what's happening from term to term there? What's going on? From 7 to 9, what do you do? Add 2, add 3, add 4. So what is it? You might be tempted, I don't hear anybody saying it, but you might be tempted to go arithmetic. But careful, it's not arithmetic. Because it's not adding the same number every time. Remember, it's got to be, it's not just that it's a pattern. I agree it's a pattern. But it's not adding the same number every time. Huh? So it's not arithmetic. It's not geometric. This is a neither. Right? It's not adding the same number every time. It's not multiplying the same number every time. It's neither. Now, if you want something interesting, if you go down one more layer, it is adding the same number every time. 2 layers deep. Do you know what that means? That means it's in squared kind of formula. That's not in this class. We're not going there. But there's always more math if you're interested. When it's 2 layers deep, constant, that means it's second. Right? If you go 3 layers deep and then you find a constant, that means it's the third power. Anyway, this is neither. All you got to say in our test is neither. It's neither arithmetic, it's not first power, and it's not exponential. Off quick, but it was geometric. That was right. Let me show it again. There it is. In power. Geometric, right? It's exponential. And then you got to find the first 50 terms, and I don't got time for that. We've done it before. You know how to do it. All right, what about that one? Minus 327, minus 243, 2187, da-da. What do you think? Arithmetic, geometric? Yeah, it's multiplying, what, times negative 9? times negative 9. You check it out on your calculator, it is. So, wait, isn't it? Yeah, it is, yeah. So it's multiplied by negative 9 every time, even this time. So it's geometric, and you got to find the first 50 terms, and I don't got time for that. So I'll move on. All right. 5, this is the last section that, other than trig. We start trig next week. Trigonometry, and it's trig to the end. Our last 3 weeks are all trigonometry, which you had before, right? That was a prerequisite for the course. So we'll do a quick review of trigonometry in the last 3 weeks. This is our last topic. It's not trigonometry. It's trigonometry after this till the end. 3 more weeks of class, and then finals week. All right, so this is the last, like I said, the last non-trigonometry concept, binomial theorem. So what I want to do is I want to be able to take x minus 3 to the 6th power. X minus 3 to the 6th power. That's not easy. Somebody want to do that? I don't want to do that. Don't write this down. Let me just start and show how terrible it would be to do the whole thing by hand, so that then we'll all appreciate the formula. Because that's basically what we're getting. We're getting a shortcut formula, so you don't have to do that. You don't have to FOIL that out, right? And they can make that power 10 or 12 or 15. You know, right? So even 6 would be a pain, right? I'd have to FOIL these two. What would I get? X squared minus 6x plus 9. And then maybe I could FOIL these two. X squared minus 6x plus 9. And FOIL these two. X squared minus 6x plus 9. But then I got to multiply these two. Boom, boom, boom. And that would be x to the 4th minus 6x cubed plus 9x squared. Then this guy will go to all 3. Don't write this down. Hope you're not writing this down. Minus 6x cubed. I lost my place. Minus 6x cubed plus 36x squared minus 54x. Then this guy, I'm not even done with the first one here. Plus 9x squared minus 54x plus 81. All of that. And then when I get done with it, I got to go times that last one I haven't done yet. Right? I mean, this is getting awful. And that's just 6th power. And as you go on in math and science, you need to have, a lot of times things will come up where you have two things called binomial, two things in a parenthesis, like an x, and in this case we have an x and a minus 3, to some big old power, and you want the final answer. And you don't want to do it all the way out with a million FOILs. But you need the final answer for things you're trying to do in math and science. So we need a formula. So that's what the binomial theorem is. It's a formula for how you can quickly jump to the answer. Oh, my pen just died at the very end. That was bad timing. I thought I could make it. Let me charge for 30 seconds. So we need a formula. Let me just say this while it charges. We need a formula that will be able to handle whenever you have two things. And it doesn't have to be an x and a 6. It could be like 3w and plus 7z to the 8th, all to the 10th power or something. So anytime you have two things to a big old power, you need a formula that'll jump you to the final answer without writing 10 of those parentheses and foiling it all out with tons and tons of work. We need a formula that will do that. So let's take a look. So instead of all this stuff that I have here, there we go. Let me erase all this mess. What's that?
Yeah.
Oh, I got to plug you back in. There we are. Okay, so let's try. Let me show you the formula. All right. Okay, so I'll give you the formula, the binomial theorem. In fact, let me just go grab it for you. Okay, there you go. Yeah, so there's the binomial theorem. Just, you see that's two things to a power. Boom, there it is. Just use that, or you can just use this version, and you've got it. Make sense? Can I just leave it at that? Questions on that one? I'm just kidding. I'm joking with you because I want to make another point about math and science. You can't read the books, can you? I mean, that's like crazy. That looks like Chinese, doesn't it? Right? That was always my experience when I read. I always thought this way. I thought math books, they're not really written for students. They're written for somebody who already knows the stuff, it feels like, right? I would always read this kind of stuff when I was taking different math classes, and I would go, really? Are you trying to help me? Because it doesn't feel like you're trying to make it clear. You know, it's like they're just writing stuff, you know? I mean, who's that for? And not for somebody trying to learn it. All right, so we're not going to do that. I'm just sort of joking around. But also, I am trying to make a point that,
Are those being divided in some?
yeah, I'll show you exactly. Wait, I don't want that one. No, that's not the one I want. I'm tired of that one. That one. Let's go back to this one. All right, let me show you. I mean, you can click on the help button. You can get all this up. But let me just show you. What you want to learn whenever you're doing, you don't want to use those big old honking formulas that are confusing. You want to see the pattern. Let me give you the pattern. You start, we'll have time for a couple of these. Yeah, so you'll be able to do two of them. So you start with whatever that power is, 6, in this case 6. You grab that power. You grab that power and you put in parentheses, which I'll explain in a minute. It's not really a fraction. It means choose. You have a NCR on your calculator. If you can find the NCR button. NCR. Now on the TI-84, you got to hit the math button, and then you got to go over like 3 times to the PRB, the probability screen, and then go down. You'll find NCR. So you would hit 6, do the NCR, then 0, and then enter. Is how you would do it on the 84, or on the TIs. So the handheld calculators and somewhere else. You can do the NCR button. I'll show you some other ways to get it as well. And it should just come out 1. 6 choose 0 should come out 1 if you're doing it on your calculator. 6, and I'll explain why and what it is. I'll show you by hand. I'll show you by Pascal's triangle as well. So 6, 0. But let me get back to the main pattern. If you're finding that, under the math button on the TIs. Go under the math button. Go all the way to the right like 3 times. Find the probability screen. Go down the probability, the PRB, to the NCR. And you got to do the first number, then go the math button and find the NCR, and then the 0, then enter. And you'll get your answer. It's 1. Okay? So, and it's other calculators at different places. Be glad to help you. Come up after class if you're having trouble finding that, and I'll show you where it is. But let me go back to the main pattern. So you start with whatever their power is, 6, 0, and then you go up by 1 every time. This is what that binomial theorem was saying. 6, 4, 6, 5, 6, 6. So you just start at whatever the power. So if they gave me a 10th power, I would start at 10, 0, 10, 1, 10, 2, 10, 3, all the way to 10, 10. So you start with the 6th power, you start at 6, 0, 6, 1, 6, 2, 6, 3. You can crank all those out on your calculator. Now, but before I crank any of those out, let me show you the rest of the pattern. Then you grab the first. You have 2 things here in the parentheses, right? The first one's an x. The second one is a -3. You need that sign with it. And you just put x, -3. X, -3. Leave room for powers. We're going to put powers on them, different powers in a minute. But at first, just write x, -3, x, -3, x, -3. So here's what that formula was saying. So you start with your power, which is 6. You go 6, 0, 6, 1, 6, 2, 6, 3, 6, 4, 6, 5, 6, 6. And then you put the 2 things, there'll always be 2 things, binomial theorem. This is only for 2 things, which is actually very useful. Binomial theorem, 2 things, x and -3, put them next to all of them. Now, you got to put in the right powers. What powers? Again, start with 6. Whatever power you had in the parentheses. 6, and then just count it down. 6, 5. I'm just doing the x right now. Just the x. 6, 5, 4, 3, 2, 1, 0. And then start with the -3, the other one, right at the top. And instead of starting with 6, start with 0. And count it up. 0, 1, 2, 3, 4, 5, 6. There it is. We just did the binomial theorem. That's what that big old formula was saying in Chinese. It was saying that. It's just a simple pattern. So that's the point I'm really making. When, in math and science, you always want to keep going until you see the pattern. They're always about patterns. Always about patterns. Just keep working. Don't try to like raw memorize really ugly theorems. You know, it's just so hard. Math and science is so hard that way. Just keep working until you see the pattern. So much easier. All right. So now, 6 choose 0. I still remember when I was at Cal Poly, I had a roommate, my friend, and he was taking calculus, like I think it was his second or third try. He was having a lot of trouble with calculus. He kind of like had to pass it, or he was going to get in trouble at Cal Poly. Anyway, and he was a construction management major. It was just his last math class. They make them take Calc 1. Anyway, and I remember he was like, where he had to memorize this big sheet of calculus formulas, or it was a big formula thing. Anyway, I still remember Mitch, and Mitch was like, Brett, can you help me memorize this thing? He asked me one night if I could help him learn the thing. He was having a lot of trouble. So I remember sitting down with him at the kitchen table, and it had this big old sheet of calculus formulas the teacher, his calc teacher at Cal Poly, had given him to memorize for this test. And I saw the pattern. I mean, there was a pattern there. I was just trained, because of all my math classes, to look for patterns. And I showed, like I just showed you the pattern. I just said, look, Mitch, look, see how the number goes, dun, 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 dun. We spent about 10 minutes doing it, and then he's like, I got it. I could do the whole thing. He had that whole sheet memorized, not because he really had it memorized, but because he had seen the pattern, had understood the pattern, and then he did fine. So that's it. In math and science, keep going until you see the pattern. It's so much easier. So much easier. All right. So anyway, we got to do these 6 choose 0 things and these other things. So what is 6 choose 0? You can, like I said, you can use your calculator and do the 6C0. You'll get 1. I'll show you by hand as well. Oops. By hand, what it means. It means, am I on the wrong thing there? I am on the wrong thing. Yeah, there we go. 6, 0. Let me write it down here. I'm running out of room. 6, 0. Well, I'll put it over here. 6, 0. Oh, I don't want to do the 0 because the 0 is weird. I'll come back to the 0. Let me do like 6, 2. 6, 2. What does that mean? That means start at 6. If you want to do it by hand. If you guys have a calculator, just do it with your calculator. That's fine. Don't worry about it. If you want to know by hand, you start at the first number and you do 2 numbers and the bottom number all the way to 1. Did I say that too quick? You start at the top number. You do the bottom number of numbers. Does that make sense? So you start at 6, do 2 numbers. Going down, like factorial, going down. So start at 6, do 2 numbers. So in other words, at 6, 3, I'll start at 6, do 3 numbers. At time, they're all times. 6 times 5 times 4. See, I started at 6, did 3 numbers. And then the bottom goes all the way to 1. Does that make sense? The top number is your starter. The bottom number is your number of numbers, at least on the top. And then the bottom goes all the way to 1. It's factorial. So that's what? 30 over 2, 15. This one's something else. Oh, 6 cancels. Right? So 15, 20. So anyway, use your calculator if you want, or do it that by hand way. However, what you'll find is 6 choose 0 is 1. 6 choose 1 is 6. 6 choose 2 is, we found it right here, 15. 6 choose 3 is 20. You with me? We found it right here, right? Or you could use your calculator. Once you get to halfway, I'm halfway, they repeat. Descending. 15, 6, 1. Don't even need to do them. See the pattern? Once you get to halfway, there's patterns in everything. That is math. I know I've said that a million times, but it's so true. Math is patterns. See the pattern, and it's so much easier. And now, is that okay to there? There's also, by the way, I'm showing you so many different ways. I'm probably confusing. There's also Pascal's triangle. You guys seen that? I'm sure some of you have. Pascal's triangle is a nice way to find all the coefficients as well. Pascal's triangle is where you start with the ones. Pascal was a mathematician, philosopher, astronomer. They always did everything back in the 1600s, whenever he was around. Anyway, you do ones down the outside, then you add to get the middle. So 1 plus 1 is 2. This one and this one added to be 2. And then, so any 2 numbers add down below them to be the number between them down below. So 1 plus 2 makes 3. 1 plus 2 makes 3. And 1 and 3 makes 4. 3 and 3 makes 6. 3 and 1 makes 4. See that? Do one more. Put a 1 on the outside, 1 on the outside. 1 and 4 makes 5. 4 and 6 makes 10. 4 and 6 makes, it's supposed to be a 10. Oh, I'm running out of room, aren't I? I'm not doing very good. I'm going to redo Pascal's for you with a little more room. We'll do it up here. 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. Hopefully that's enough. Pascal's, this is enough. I'm giving you 3 ways to get these coefficients. This is 2, 3, 3. You know, like I said, these add, these add, these add 4, 6, 4. These add 5, 10, 10, 5. One more. I'm running out of room. Must be a 1 out here, a 1 out here, and a 1 out here. 6, 15, 20, 15, 6. There's our coefficients, you see. So that's another way. You can just do Pascal's until you go down to the right level. All right, I've given you a million ways to do this. So those are them. We need more, though. There's also the x to the 6th, and minus 3 to the 0 is just 1. Multiply those together. X to the 6th is the first term in the answer. We're almost done. Let me just wrap this up. That's the first term in the final answer to foiling out 6 of these. The next one, x to the 5th times minus 3 to the 1. So that's minus 18 x to the 5th. Oh, it's off the screen. Huh? Minus 18 x to the 5th. Next one, it's 15 x to the 4th times 9. What's that, 9? 135? 135 x to the 4th. The next one, these are maybe these too big. X to the 3rd times minus 27. Was that minus 540? X to the 3rd, that's totally off the screen. There we go. Do you guys see what I'm doing there? Am I losing you? I'm multiplying whatever numbers I got from Pascal's or by calculator or by hand times the minus 3 to the power thing. Right? Next one, what was it? 15 x squared times, what's that? 81 minus 3 to the 4th is 81. Somebody got, what's 15 times 81? 1200 something. 1215? Thank you. 1215 x squared. And next one is what? 6 times x times, what's that, 243? What's 6 times 243? It's, I don't know, 729 double. 1458? Next, oh, negative. Is it negative? Oh, yeah, negative, because it's negative 243. Thank you. Negative 1458. Last one is 1 times x to the 0, which is 1, times some big number, 81, 729. So I think it's just 729, right? There it is. There is the answer to the whole thing done. Now, it gets a lot quicker after we do more. So this is not due. We didn't finish it. So just 12.3 is due. We'll finish 12.5 next time. Have a good weekend, guys. I've got old tests if you're missing the test or something. I've got them here. If you had trouble with the calculator getting the C in CR, come on up. Be glad to help.